Okay, great. So hi everyone, my name is Mario. I'm now entering my fourth year of PhD in the CDT at UCL under the supervision of Ingo Waldman, my first supervisor, and I'm going to discuss today the placement that I did during my third year and with Jasmine Grimsley, and which was at the Joint Biosecurity Center, part of the Department of Health and Social Care. So I think we've got around 20 minutes for the main talk, and then a few minutes for discussion, if I'm not wrong. So I'm going to go through it, talking maybe a bit of background first, my background and how I got to do this this placement. Then we're going to discuss the context of the work itself, and finally discuss a bit the placement and how useful it is going to be for me in the future. So yeah, I hope that this is going to be triggering some thoughts and discussions. So feel free to ask questions. Okay, so I'm trained as an engineer in data science mostly, and then I switched towards astrophysics. I say switch, but actually try to find a middle ground between both. And after 8 months working in a data science consultancy company, I found out about the CDT with projects precisely merging data science and astronomy, and so that was perfect for me. And so I decided to join it, and so I'm currently in the exoplanet subgroup of the astronomy group at UCL, working on exoplanet light curves, trying to find transits and improve methods to detect exoplanets and to characterize them. By the end of the second year, I heard a call from the management team of the CDT here for a possible project at the Joint Biosecurity Center, working toward the COVID-19 response, and I was quite curious about it. It was quite general terms, in terms of analysis of outbreaks or wastewater data. I wasn't very precise, but never mind. I just started talking and then found it was interesting. So I in the end, I started in October 2020. And yeah, that's how it started. And I guess, yeah, this project was mainly appeared because of the pandemic itself. There were a few projects related to the ONS, Organization for National Statistics, that my supervisor was part of. So we were already in communication with them potentially. But this precise project really appeared because of this. And I think that then there was a group project related to this. That's just a bit of the context. But yeah, that was really related to the pandemic. And it ended up being mostly centered around wastewater-based epidemiology. There were plenty of data science-related projects at JBC and in government towards helping to model the pandemic and help decision. But this was a kind of a novel project based upon the analysis of environmental data, in this case, more specifically the wastewater-based epidemiology. So there's several things in environmental monitoring. We can monitor air or water, and wastewater is something that we are monitoring. Countries are more or less monitoring for different reasons. It can be detecting toxic substances or the use of medicines or different things related to health, and there's a wealth of different things that it can be useful for. And in case of wastewater monitoring, the easiest way to monitor or to take measurement is to go directly to the sewer network and take samples there directly. So that's how most of the data that the UK is acquiring is coming from these sewer treatment plants. And so, as everybody's aware, there's been this COVID-19 era crisis, which started in December 2019, and just a few months later, there's been a worldwide endeavor towards trying to monitor and detect COVID-19 and SARS-CoV-2 virus in wastewater. So this happened in different countries in the world, and really quickly, it was shown that we were able to detect it and make use of it to to model it as a complementary source to the classical testing. So that's really interesting because it's complementary. It's not meant to replace the classical testing, individual testing, but there are several advantages, such as the fact that it is thought to be sensitive to non-symptomatic people. And also we can monitor large fraction of the population passively without any privacy issues. And so there's plenty of advantages which make it potentially a really interesting tool and going forward as well when the mass testing strategy will end. So the English program really started more towards the summer of 2020. That's where when the data that we were handling started in June, around June or July 2020. Then there was beginning of sequencing of different variants on our data, which made it more richer, and also it went with the different efforts towards trying to detect variants, which is mostly the current concerns now. It's not it's about whether we can detect variants or not. It's an important pillar at least, and gradually as well, which is interesting to notice. There has been an expansion of the program, which initially was maybe 20% of the population, which was covered nationally when I started in October, and by April 2021, 71% of the population of England was covered, which means that we were collecting data weekly, and this data covered 71% of the population. So that's the general framework about wastewater-based epidemiology, and this can be simplified as well. The general picture like this: we have a population, and with a human feces which are emitted in the toilets. They go in their discharge in the wastewater sewer system, and there's they get diluted with different things. It can be industrial discharge or different processes. So there's definitely geospatial variations here, and then we measure them in the sewer after a series of different steps, and finally the samples are analyzed with some form of variants of PCR testing, and from this we can use it to model the fraction of people infected. That's the ultimate goal, and yeah, that's a kind of the circle of wastewater-based epidemiology. It's a really complex problem, and which is still ongoing. It's not been solved completely because of these different confounding factors. And here, it's just a table that we ended up doing to try and identify what could be the main sources contributing to, and which one we had data for. So if in the end, we measure the virus concentration, that's our data, and gene copies per liter. The initial variable that we're mostly interested in is the proportion of SARS-CoV-2 infected population. And in the end, there's different things which happen in the network, in the sampling, and in the analysis of these samples, which make it potentially noisy, potentially confounded by a certain number of factors, and that makes the whole scientific question, the inverse problem, complex. And just to have a little picture of the coverage in England, that's all the sites which were on from April 2021, and which cover mostly the urban areas, which are still monitored at the moment. Okay. So really quickly when I arrived, it was a new project starting in the Department of Health and Social Care. And there were very few analysts in this team dedicated to the wastewater analysis. And really quickly, they had started already for a few weeks and months to acquire data. There was a urgent need to visualize the data. And so I was asked really quickly to do a dashboard, a visualization dashboard to relate the time series of data that we see on the right for each site to the different sites, and have some indicators, some colorful indicators about the level of risk, which is which can be compared to a certain statistical measure of concentration. What we would like also in this kind of dashboards is to be able to relate it to other sources of data. So the top time series here is the test and trace, so the number of people infected, the number of cases in the given area. So really quickly, we had this dashboard, which enabled us to visualize and communicate it, because one aspect of this project is that we weren't only working as a group of scientists, but the goal was quite often to be able to communicate it with people in government, with decision makers, etc. So the visualization aspect and the ability to provide tools for anybody to be able to understand quickly the problem was paramount. There were different sub-studies that over the placement I was involved in, some of which were more focused on local analysis. Some others were actually an important part maybe was to cross-match the wastewater data with other sources of data to validate the potential of wastewater data with other epidemiological indicators, such as the REACT or ONS studies. And yeah, there's several other smaller scientific projects, such as the study of the flow variability, the cadence measurement, how many times in a week should we measure so that we have statistical threshold passed. The lead on lag analysis, is our data before or after the testing, the classical testing? How uncertain are we about these measurements? And finally, maybe the last few months were more dedicated towards building regression models from all the data that we had acquired in the several months, how to derive to infection rates from wastewater data. And that's what we are going to discuss for a few minutes now. And so we could wonder, where do we want to build regression models in here? And maybe one of the first thing is to be able to translate these concentrations to more interpretable quantity. We're not really interested in number of gene copies per liter. Nobody really can relate to it except maybe an expert in wastewater epidemiology. But what we're interested in instead is the fraction or the number of infected people in a given area, and this evolution maybe. So building regression models, that's one of the first reasons why we want to do this. And then it may also help us to understand better the wastewater data and the nature, the differences with the other indicators that we have, given that we don't have any ground truth for the number of infected people in a given area. So what we'd like to pinpoint the relationship between these different indicators that we have, or to constrain some biophysical quantities, or the R number, for example, which was often communicated in the media. And finally, the ultimate goal was to help response and for example, identifying places diverging from the test and trace program and other kind of data. So this is just motivation. And what we had in output of our model was other indicators of prevalence or incidence, such as the pillar 1 and pillar 2 cases, which is basically the classical mass testing strategy. And the other one is the coronavirus infection survey, which is supposed to be less biased. So in the end, I was trying to focus more on this one. They have pros and cons, but the second one is less biased. In input data, we have the concentrations, which is here in bold, but also lots of covariate data, whether it's specific to the location where the samples are taken, or even specific to the samples, which can be the pH or other indicators, which can be useful to account for the confounding factor that we discussed a bit before. So all this is really important if we want to build models as precise as possible. And so although our samples are local, we we want to build models which are global to take advantage of the full data set. And also we want to build, we account for the regional differences and the sites differences by using either hierarchical coefficients in linear models, which can be called random effects model, which are basically linear models, but with coefficients which are shared by some groups. But we've also tried some other models, amongst which nonlinear models such as gradient boosted regression trees, which can model the regional differences using metadata, such as the population in each site, etc. And in the end, and finally, we used bootstrapping and then cross validation to validate the performance of the models. Here's just one picture of the predictions on the test set of that the model provided. So in dark here is the actual ground truth data from the coronavirus infection survey with confidence intervals, and in blue the prediction on a test set bootstrapped. That's how we got also the error bars. And this has been averaged by regions. This is often how we present the results in here. And we can see that here, from the wastewater data, we're able to build models which follow quite well, which at least fall in the confidence interval quite well of the coronavirus infection survey. So that was quite useful, and this can be then extended to do some forecasting, even though that's not the main point of these kind of models. It gives some confidence. And one other kind of thing that we can do with these regression models is to do some lead and lag analysis. What happens if we shift the input and not the output in different cases? Can we improve the model performance? And this was the case with the test and trace data, which enabled us to suggest that there might be some lead from the wastewater data on the test and trace data, but this wasn't the case in the coronavirus infection survey. So that was a quick overview of the work actually done during the placement. So it was mostly different piece of code and presentations and a few scientific reports and publications which came out of it, and this is really work ongoing. There's now the team has grown significantly, and there's several analysts in the team, so it's really interesting and to see how it's continuing. And also it has a potential to go beyond just COVID analysis. This can be replicated potentially for other indicators, other viruses, and other things in general related to healthcare. And I think this is something which now governments are really aware of. They realize the potential that there is in analyzing wastewater. And I actually mentioned it here. So wastewater surveillance can be used for pathogens, use of medical products or environmental stressors on human health, and can be combined with other environmental indicators such as air and water more generally. Okay, I hope we still have a few minutes for some input into the discussion. I'd just like to mention maybe about the work that I've been doing there. It was mostly lots of emails, lots of meetings, to get to know the team, but also because there were many different actors involved in this displacement. There was a lot of data handling as well, taking different sources of data, putting them together in the right place, working with the data architects, and building pipeline for the analysts, doing some reporting every day. And in the end, the machine learning aspect and the statistical analysis and the scientific writing was occupied a small fraction of the time overall, which I don't think is uncommon, but still interesting to stress again here. Obviously, it was during the pandemic, and so it was mostly working from home. Actually, all the work was done from my home, which had pros and cons, because I think Yes, it's a bit harder to manage a work-life balance, a healthy work-life balance, but also it's easier to meet lots of people, and we've been in meetings with people from Scotland, from Wales, with whom they have really similar programs, which are, or even European meetings, and there's dozens and hundreds of people that we've been meeting daily or weekly, and this was made possible by the fact we were all working from home in a very efficient way. About the placement, I think it's been really interesting for me in different aspects. The fact that it is a real life contribution with positive impact. Not that astronomy doesn't have a positive impact, but it's maybe more indirect impact and also less day-to-day impact. So that was I think it gives a nice feeling when we think that the project we're working on potentially has a potential positive impact. It was interesting to witness a mixture of civil servants, academics, and contractors and professional contractors working all together towards this goal, which is trying to help and their little bit towards solving this crisis. But yeah, really interesting to witness this from an inside, and how scientists can try and collaborate with policymakers on a very short time scale to provide to give an answer, or to try and take the best choices. And yeah, it definitely opened my mind and gave me an experience related to data science for public service and public good. And also, I'm not completely sure exactly about how I want what I want to do later on. That's definitely going to be helpful in my balance because of this experience. It's easier to have an idea of and project oneself into something if we have already done something, I guess. And yeah, so just a few general conclusions that I think the placement is a great opportunity to explore different structures, different applications, and work with different people. And that's definitely been the case for me. And I think in every different placement, it's naturally going to be somehow different in some of these aspects from the day-to-day work we're doing in academia at a university. And most of the time as well, it's really useful to try and address partially the eternal question, academy or industry. But yeah, so this has been useful for me, and I hope it's been also useful for you to hear this witness. And if you have any questions, really, whether it's now or later on, please feel free to ask. Thank you.